Good afternoon, gentle readers. Today, the 22nd of June, 2024, is a bright, warm, and sunny Saturday afternoon in Seattle, Washington. I should like to thank YouTube, this channel or website, as it were, for hosting these videos graciously, gratuitously. It's a common sort of means to preserve, present, and store videos of quite extended duration. Once upon a time, it was 1995 or 1996, and MPEG video was the first digital video after the usual idea that television, color television, lived on 6 megahertz or so bandwidth per channel with regards to the way that television signals in their interlaced form of sorts and with regards to the standards like NTSC and PAL and the ATSC standardize color television after black and white television channels given over the air televisation of television back in the day with a square rectangular aspect ratio and these kinds of means. Then in these times, like in the mid-90s, then the Moving Pictures or Motion Picture Experts Group, cousins of the Joint Photographic Experts Group, arrived at standards for the file format and interchange of video data, moving picture plus audio, and that the MPEG-1 was designed to operate on basically a 1.5 Mbps carrier line or a T1 line. And so back in the day, that it was kind of like so that where other image file formats, for example, like GIF, as it were, was originally designed to store television data in moving picture frames, and it has a very brief sort of run length encoding, and it has some extensions and what. Then MPEG-1 became this standard for standard definition, in a sense, television, and later MPEG-2 is associated with HD TV and these kinds of things. MPEG-4 associated with more interframe prediction and some various aspects of the features where these image file formats basically store frames and then they interpolate between the frames, frame to frame, as with a separate audio channel or track synchronized with then these frames. That these are standards for the video, and they are incredibly and completely ubiquitous and just standard. Like if you point a satellite dish to many satellites in the sky, they will send down JPEGs or MPEG video. Anywhere on the internet, any of this H.264 broadcasts, H.263, this, that, of the teleconferencing is almost all entirely vis-a-vis this one set of standards and specifications. And that includes some other upstarts like various organizations, everything from Flick video format to WebM or what, that by and large it's all completely this standard kind of way, vis-a-vis something like Apple's movie format, or that being just a container for any of a wide variety of multimedia file formats, and these other kinds of developments that over time arrived at that to serve one video channel 30 years ago cost thousands of dollars a month at least. And to get like a license to and enough bandwidth to serve like 3 or 4 video channels at a time was incredibly expensive. So with Murphy's Law, or excuse me, Moore's Law, kind of doubling bandwidth and CPU and even memory, it got to where they originally designed then for HDTV that they would be digital, and the original HDTV televisions could not exist because they did not yet have chips big enough to support them. But years in advance, they were designing things so it would kind of be like so. And then years given the doubling and the doubling, you must have heard of this game about the man who won a prize from his patron, and he said, "What do you ask?" He says, "I just want a chessboard and 1 grain of rice." And on each of the other pieces of the chessboard, each of those squares, just twice as much rice. With 2 to the 64 or 2 to the 65 rice, and that's too many for it to be supplied, vis-a-vis something like the sand reckoner or something like that, which is a traditional thought experiment of counting or at least estimating all the grains of sand in the universe. So before they could have HDTV, it so had to arrive that they had to invent a television with enough processor capacity in the CPU to get enough constant rate throughput to make this so. And it results that there were tens and tens of thousands of dollars for one of these TVs, 20, 25 years ago. And then so when they actually had one, it was a pretty big screen, and then they had various technologies of the screens, like after the cathode ray tubes end, vis-a-vis Philo T. Farnsworth and General Electric and RCA and where televisions came from. These are square televisions, not round televisions, which are a different sort of story, the round monitors. That at this point in time, then HDTV became a thing, digital television became a thing. And it was really only as with regards to this embarrassment of resources, computing-wise and transmission-wise, that it was made possible to do so. So that these days, the capacity of one of these internets, telecom giants, like this YouTube, has it so that they can surface just a tremendous amount of media. And then with regards to the edge networks and content distribution networks, that once something's recorded, then it's pretty easy to just treat it like as a stream of bytes, and as constant data. And then the customers kind of pay for the bandwidth, and it is to arrive the last mile or what. And then you have it so that a given smartphone for at least 10 years or so is able to play HD TV. I mean, the capacity and the output of the smartphones is not much really different in the last 10 years, surprisingly, except as with regards to all this higher Wi-Fi, Bluetooth, 5G stuff, making it so that the back end can just be incredibly noisy all the time without anybody really noticing. The camera's improved, say, but otherwise it's pretty much the same platform as 10 years ago. That all these standards and specifications of technology make it for it's a very fungible type thing, and what are the tremendous amount of resources which would have made it possible for anybody to broadcast anything at all these days is within reach of an average person. So yeah, that's great, and I like to thank YouTube then basically for making it so that being part of Google, I guess, that G for government, FB for FBI, G for government, that it's kind of a thing, that it's made it very simplified to distribute videos like this. That said, now if I noticed the other day, if I mentioned global warming, that will pop up a little sign saying global warming, and it kind of amused me, and at the same time it just kind of outraged me. It was kind of like, are you going to put a verisimilitude detector on everything and put it up something so like basically according to voice stress analysis, the perceived veracity of the speaker is or is not inclusive of the truth? Maybe not. But that's just an example of something that could be a value-added offering for many kinds of people to have on the output of your computer or something along the lines of a little red or green light that basically estimates whether, according to voice stress analysis techniques, that according to the science of voice stress analysis, that the speaker's perceived veracity of their statements is or is not so. All right, well, enough of that. So today is June 22nd, 2024. And it's about 4. And what I should so hope to do today is some more about the swath. So we have in this dialogue a concept called sweep. And so sweep is a function. It is the natural integers as if shrunk to the unit interval. They range from 0 to 1, and it is a model of the unit interval 0, 1. So sweep is a non-standard function because it's not, as with regards to the complete order field and the Archimedean field, and at least one model of the real numbers, that it must be anything except some different model of the real numbers if it is a B1 at all. And the transfer principle relating that all the same properties arise and hold of a continuous domain that need to be developed for themselves. And contradictions, one way or the other, when they put together in one theory, have to be made so that there are no contradictions. This is all one theory. These are not competing theories. These are combined theories that have to be one theory. So sweep for a long, long time was kind of put down as saying this Aristotle's other continuum, because it's nothing really new. I mean, it's the same issues that come up forever and ever. It's just kind of having been arrived at one opinion for the linear curriculum for everybody to arrive at a manner of speaking where they're all talking the same way and that they all agree to the same things. Because maintaining all the way along the back and forth of all these things to have both clock arithmetic, sweep the function, and line reals, along with the complete order of field, the Archimedean, and what results for delta epsilonics, particularly neatly the field reals, all for one analysis for algebra, arithmetic, geometry, function theory, topology, operator calculus all around, analysis all together, number theory, mathematics. That so the sweep then is well defined here, and it's well defined vis-a-vis its standard, real, analytical character. It's special, central. It's even fundamental. It's the continuous and discrete. They're coming and going together and apart. So, it is a very, very essential concept related to anything to do with line elements of a line integral. These line reals, what are called iota values, for iota being a smallest positive value, and then their product altogether of them by an infinitude that they are so defined by is equal to this unity then that it defines for all such manners of form, proportion, magnitude, and the regular in geometry, exactly 1 and exactly the range between 0 and 1, the sweep between 0 and 1, this natural unit equivalency function, finito. So, in the development of the consideration of that gets into a lot of what goes on with Zenos' arguments about the cases of constant velocity, constant uniform velocity, and constant uniform time. So by constant uniform, it's meant equi-distributed and equi-partitioned. It's not just enough that the integers are each different, and that they, as in the unbounded, they always count back down and make each integral moduli. They have to make all of them. And then it works out to the infinite. There are multiple laws of large numbers. There are at least 3 ways of looking at the space of all the sequences of zeros and ones with a beginning and no end, and unbounded and infinite. This sparse Cantor space, square Cantor space, and signal Cantor space to reflect on these at least 3 continuous domains, the field reals, line reals, and signal reals, respectively, about the anti-diagonal argument for uncountability, and this only diagonal argument, or directly diagonal for the non-Cartesian function of the line reals, so that they even all fit together in standard ordinary set theory, being a thing, together, and having a common milieu, and uncontradictorily. So that being the setting where in our mathematics we have at least this richer accoutrement of continuous domains, then the idea that has got into is after Zenos' setups of constant velocity and the geometric series and the infinite limit and the sum of the infinitely divided, where the infinitely divisible is a thing from any finite means going forward, and the infinitely divided is its ultimate, if not penultimate or ultimate thing, the finality of it, after this first principles and final cause, the meeting together, meeting in the middle of nowhere, that these deductive results as analytical bridges are the only thing that so offer, and everybody sort of needs, or else they're in a sense, not having developed a more thorough meta-analysis of their own critique. That after that, then there was consideration of motion, and so again, just like the numbers and their nature, the nature of motion and mechanics of motion is an ancient study, and it is reflected largely on what people ascribe to the Galilean for Newton's laws, for then Newton and Leibniz as being whatever is argued classically and super classically, as that Newton ends up being kind of classical and from the finitist view, and Leibniz ends up being kind of like the super classical, and both of them, I suppose it can be said, came up with the usual fundamental theorems of calculus. And if Leibniz kind of by treating the vanishing quantities as algebraic, and Newton as rational, that it is as well that either way, real analysis is its own thing. That then for motion, we get into the V motrix and the V viva, or the passive force in a sense, and the active force. And so here that was discussed as with regards to a number of different notions, and including things like the javelin or the spiral, and why that's a real thing with regards to space contraction and momentum, and really what it means in terms of the inertial, that mass times velocity is inertia, and that the mass times acceleration is force. So mass times velocity squared, or half of that, is a momentum or so, with regards to that being just kind of a term and it's first in its power series, and then why otherwise there's the whole rest of the infinite power series that was terms disappeared because it's the first term that dominates. With regards to that in the nonlinear and the highly nonlinear, eventually it doesn't, and it basically becomes, after the study of means, that the big end and the little end at some point in time switch sides. That the V viva and V motrix then became that for Newton's laws and Galilean laws, in the most usual ways that people think about things, it's just things that rest stay at rest, things in motion stay in motion, and equal and opposite. And then with regards to gravity and inverse square and force equals mass times acceleration, two different things. And with regards to the equivalence principle and relativity and the acceleration of gravity being within a rotating frame and the acceleration according to linear acceleration, two different things. The equivalence principle and a deconstructive account of the equivalence principle of general relativity in non-terrestrial settings. And furthermore, non-terrestrial orbit or sidereal settings. Well, of course, classically all in the middle is quite close in the same. With regards to that on Earth, in the usual terrestrial setting, that gravity is just down, and the same as a linear acceleration is up. So that then with regards to things like the centripetal and centrifugal, and the idea that the rotating frames are free to rotate forever, vis-a-vis what goes up must come down, and the idea that it's not a perpetual motion machine instead of generating work. It's just a closed system with nothing coming in or going out. It's just a perfectly spherical ball spinning, and as with regards to a lack of friction on a contact surface, it has no given physical tendency or propensity to have resistance to its power, in a sense. With regards to the Mertonian school in Oxford, and hundreds of years before Galileo, and 100 years after the Islamic Enlightenment, or Averroes and Avicenna and such, what became of the great advent of the continental schools and the Enlightenment, of what later became then mechanics, and then later became quantum mechanics and relativistic dynamics, for the very large scale and the very small scale, and vice versa, respectively. So and then with regards to the swath is what we're kind of leaning to. So from sweep is first is continuous and discrete at all. And so Zenos arguments make for the geometric series and the infinite limit and all these things which are expected to be known by any analyst, by anybody who studies real analysis or dynamical modeling. Not as with regards to anything wrong at all with concrete mathematics, finite combinatorics, law of small numbers, and the usual most obvious law of large numbers with regards to the law of small numbers in terms of probabilistic settings and combinatorial settings, concrete mathematics. And then not to say that concrete mathematics doesn't have its asymptotics, which is its analysis in the results that end up deriving not necessarily the ratios and the quantities out of these ratios and the infinite expressions, which are real, usually mostly related to the natural logarithm and the binary logarithm in zeros and ones and the exponential. That there's then to be said for analysis that for Zenos arguments in the infinite series and this and that, and then as also with regards to pi and Catalan's constant, Euler-Mascheroni, distribution of the primes, pi squared over 6 and that, the golden mean, or phi, root 2, and these being the most familiar algebraic and transcendental constants of mathematics that arrive in many, many, many situations, that it so results that mostly it's the exponential then that shows up everywhere, because then according to real analysis it's up or down the same. And it goes without saying that the trigonometric is everywhere because it's so entirely completely well explored. It's computable from pretty simple first principles, and it was the school for thousands of years was with regards to how an analysis developed on these things. Complex analysis with the Euler's formula, which is telescoping terms like I took an infinite expression and reduced it down to just a handful, and so that's how I arrived at this thing. I just had made it so it canceled in its way out, so it gets smaller. It's telescoping in this sense. Euler's formula, and then with regards to that and the complex identity, that's just off de Moivre or trigonometric identity. De Moivre, of course, shows up in a lot of places. And with regards to sine squared, cosine squared, and 1, and these kinds of things, and sine and cosine being orthogonal and as well de Moivre's, with regards to the phase, and that being just a simple matter of two phase, and this kind of thing. That then another kind of relevant touchstone of the analysis, because these are all the tools that there are in a lot of these analyses. It's like before we start getting up into matrix mathematics and linear algebra and means of solving systems of equations and means of finding transposes and otherwise block matrix results, this was all there was in kind of a sense. So Zenos arguments were built for analysis first for the analytical setting as of, well, these both sides don't agree, how do they meet? And then with regards to, well, for formalism, we just picked at least one point and then we say they all go out that way. Or it's like we say that we're not ever going to really get there, but each one, if you chose to extend it out, it would so arrive. That is mentioned here, it's like, well, then it does, right? You know, and these ideas about the infinite completions and the infinite expressions and the infinite limits that then make for perfect values, no different than their closed forms, as it were. Thus that all these different expressions can arrive at the same thing and one thing, and not being just an entirely otherwise grasp towards something, which is always posited to exist, besides saying, well, we don't get not close enough. It's like, it's not too far, you know, that it really has to kind of finish itself off. That and I'm getting around to what is then the swath again. So what is swath? So the idea of moment in motion for the past while, and it's shown up in these talks for quite a while, as meters per second or seconds per meter, and which is kind of natural, and which is one to frame everything in, when it could be either, and it could be either in terms of each other's other powers, as many as there may be. There's this notions of the alternating and resonating dimensional alternator and dimensional resonator, with regards to that anything that's going constantly is also just not diverging both ways all the time. Not diverging the higher order, not diverging the higher order, not diverging the higher order, ... straight line. And so what comes up right out of that is then that there's constant motion, constant velocity, and then there's rest, which is kind of like zero. It's infinity seconds per meter. It's usually left right out. But then constant velocity, then there's eventually some change in the velocity for it to go from 0 to 1 or 0 to -1 or otherwise to change at all, and not just change and go on one way forever, but to, you know, to be able to be restitutive and oscillatory and this kind of stuff. So the velocity is considered as the first order derivative of position with respect to time. And so when you take the derivative of that, you can see that the change in the velocity, change in the position in one time is according to this velocity. So it's exactly related as to the power term with regards to the derivative and the integral that computes instantaneous rate of change with respect to dt, with respect to t. The differential over dt, which reads as the differential of this expression with respect to dt. Okay. So velocity is this, and then one of Newton's laws, although it's kind of like, well, the laws, do you mean rest, motion, and equal opposite? It's like, well, that's just one law. So here we're deconstructing those to zeroth laws. And then the other one is gravity. Is like, well, gravitational is a universal constant, and it's gmm over r squared, its inverse square. It's great. That's just like a fact of physics somehow. That's on the side. That's just expressing what this force is. And then force is like, well, the whatever causes an acceleration is the force. It's in its units. Whatever causes acceleration of the mass in those units is the force in those units. At any given time. It's considered that the force is just like this force is applied. And so then we get into the integral of that, and that force as being a function of time. And so it's kind of leading them all together in the same way, the force and the acceleration over time. And thus that they're kind of commensurate quantities are blinded to each other in a little bit with regards to the linear, because, well, they happen to be zero. Just don't consider a force that's not always in the same direction, but overall is in a direction, given the resistance linearly and the resistance laterally, these kinds of things. It's kind of simplified, and it's nice and neat, and it's really pretty great. So this is then getting into for the infinitely many higher order of acceleration is like, now try to consider how to apply that or remove that, and what the average is supposed to be, considering that it never really came or went. Infinitely many higher orders of acceleration to arrive at any change at all. So swath is basically like, how can we make that into a box so that it arrives at that? It's kind of like a left or right turn, an angular 90-degree turn, vis-a-vis a course of the taking an arc of a circle as a turn. And so basically for that box, how does it round the corner? How does it round the corner to go from zero difference to one difference? And then as with regards to that changing in a particular, over the application of particular distance, and that changing over application particular time. So force is a function of time is kind of what was arrived at here. It's never just a quantity. It's always as a function of time per seconds, or per second squared, or per seconds infinity for each of these come down. Last time, or a couple talks ago, there was introduced this idea that I recently learned about called the extraordinary differential equations. So I'd grown up or gone to school and studied courses in ordinary differential equations, and they're usually just mostly said that, well, they have linear solutions. It's like, okay, I get that. But then the whole idea of these extraordinaries differential equations is that it's not just d to the dx, it's like that being application of one differential. D to the dx squared, application of two differentials. It's application of fractional of those, or it's according to parameter formulation, an implicit, it's not necessarily linear, of those. So force is a function of time in any number of orders of time. And that also it's a function of direction in regards to the forces applied via this couplings, and then getting into the strain and stresses and shears of the forces and couplings of the tensors with regards to statics and dynamics, loads, and these kinds of things. Statics usually, here with regards to dynamics, and changes which are dynamics. And I'm just making this up as I go along. So when I discover something, oftentimes it'll form an idea. And so here it's just kind of coming along with that. Many of these things that are otherwise just this linear, the solution and setup, can be visualized as things that are side by side and have all these possible left and right contributions all along the way. This gets involved with this dimensional resonator as when they pile up, and the dimensional alternator is when they cancel out. So that's pretty much about what it is to it. With regards to higher order wave mechanics, being in the resonance theory, you got particle wave duality, wave resonance duality. Waves in the middle, it's waves all the way up and waves all the way down to particles. So that then we get into what is this swath, is the idea of saying, well, we have these infinitely many higher orders of acceleration, and we're going to run out of paper. So how can we say that we just kind of fit that in a box and made it like so? So I've been thinking about this a little bit, and or at least given an idea, it's something that like the mind can chew away on after a while. In the dream state, or when reviewing other material, a quick reminder, it kind of is on the front burner in a sense, or the back burner of the cook stove of the mind. And as with regards to rest and sleep and the remarkable ability of the brain during times of sleep to entertain and resolve mathematical deliberations and these kinds of things, not consciously necessarily, but leading to these sparks and these inspirations of how these things are. I was reading this book the other day, and it's Davies on super force. So what he has is written is in the 1980s there is field theory and the supersymmetric, and then also a lot that has gone on with cosmology and expanding universe and inflationary theory after Big Bang cosmology. So dynamics of the large, dynamics of the small, putting them together. And then he gets into what these days, some of that has come to fruition, like the Higgs boson. Since the time of this book, they were like, well, we're working on quark physics, muster mark, or quark physics, after supposedly it's after a Ulysses or James Joyce, or the Dubliners, or one of James Joyce's books, quark physics. That we'd have this Higgs boson is one of the supersymmetric partner particle. And when I said one of it's because these days there's considered that there's at least these three kinds of symmetries, kind of like the ordinarity, the unitarity, and this other kind of symmetry that make for why it's like Higgs boson is one way to think of being out in the standard model, but so are these other kinds. They're exactly what they are, in a sense. So that was kind of the theme of this book. And so what inspired me about it was the sections on Big Bang hypothesis, which these days is more of a Big Boom hypothesis with regards to both the steady state hypothesis and cyclic cosmology. Because for the origin of the entire universe, nothing's really falsifiable by definition. And for the entire idea of like vacuum energy or the existence from nothing out of something and something out of nothing, it's kind of super scientific in a sense. That doesn't really stop people though from making that as a model and then fitting all the data there is to it. So science, in the 1920s, they came up with Hubble, and we got Hubble, Heisenberg, and Higgs, basically, as these kinds of three classical directions. So with Lemaitre as a Big Bang theorist, and Hubble saying the universe is expanding, then all of science writ large basically used the composition and observed densities of matter and energy in the universe to compute all the rest of these things, and then to try to figure out from the unification energies, which is according to binding energies and what they observe as what are the points at which things break down in the higher energy physics, using these as constants, then what is possible to do is to estimate or provide theories where the entire content of the configuration space was an infinitely massy or proto-massy dot. The Big Bang began in a state of, according to this theory, infinite energy in an infinitesimal space. So the concept at all is non-standard in this mathematical sense. It's non-Archimedean. Although one may have heard that what's Archimedean? It's like it's infinite and perfectly rational. That here, the Big Bang theory starts with an infinity and goes to our current state. And it's on its way to zero, or flattened out. Now, in times past, I have said something like, well, since we got better telescopes and cameras since about 30 years ago, that the expanding universe is flawed. And so I also assign that to the inflationary cosmology. And meaning it's like, well, you could just, that's just kind of made up. It no longer has the wider fitting of data to all that it is. It just fitted a closed system, and the system is more open, and the more open system, the data doesn't confirm it. It's falsified by the data. So that's the redshift blue shift thing. These days they're calling it Hubble tension, but the usual media doesn't make much of a deal about how off it is, which is all the way off in a sense, in a very real and true sense. So the Big Bang Theory has this idea of like, well, it starts with the infinite and it comes down to some rational thing. So that's the same idea to how to achieve this swath. So what's the swath? It's like, well, it's taking this strip from the outside and then how to figure out, then that ends up making a flat line and its infinite completion to help express a change on a chart in 2 dimensions of 1 dimension. That's kind of all it is and what it boils down to. In terms of the units, each of these ways, that otherwise is an entirely abstract, continuous transition that makes a 0-1 transition. So that's the idea of swath. It's the sum of an analytic geometric series, like Zenos' other arguments. It's Zenos' swath that adds up to an analytical form for changes in velocity as infinitely higher order, which they are. You can't find anybody who'd end up disagreeing with you that there are infinitely many higher orders of acceleration. It's just that they say, well, once we get, 2 or 3, that's enough that we can't really tell the difference because they're 0 as far as we can measure, even though they all add up, and it only adds up as from them, from the little end. So you got the little end with all the infinitely close that grow to 1, and the big end that's 1 or 1/2, and then shrinks, that all their sum together equals 1. That it's pretty much that when I was reading this idea about how the mathematics went into then this Big Bang hypothesis and the different regimes, especially. So because the idea of this swath integral or the swath is that it's all going to be loaded up on the big end, and so it's going to, because that's where it's considered that the terms naturally live. Well, at the same time, on the other half of the long tail is infinitely long compared to that this way. See. So that then either way in reflection and symmetry about like the identity dimension or something like that it so results that either way you look at it, it's both ways to look at it, and they add up for each other and making for this infinitely higher orders of acceleration, the big end and little end, arriving at the middle, which is classical. Simple. So you take a unit line segment, you split it up into equal partitioned, equidistributed, infinitesimal line segments. You load up most of the change in the front or most of the change in the back, either way. And then it builds up along that in the line. Then instead of like a curving line that would reach an asymptote, because it's just got to reach the point, or vice versa, that it's this part of a kind of a system. Yet that it is taking these 2 dimensions in terms of these 3, in terms of putting them all together into 1. Now, I don't know that they already have one of these, or I'd just be pointing to the book saying, this is canon. And I'd be interested in something else to try to help fill a more modern and fuller paleoclassical, postmodern, superclassical foundations development. So here, this is the framing and windowing and the box that I've arrived at to start trying to put together these pieces with these notions of, energy is conserved, 4 different kinds, and this tendencies and propensities, and attenuation and dissipation, and oscillation and restitution, each way. Then with these 3 continuous domains, mathematics is a logic that's true, and then this analytical box for Zeno. So this is basically a Zeno's swath, and hoping it's something to entertain and amuse him. Well, he's on his break or something like that, as far as I can tell. So we should turn to some books in a minute here. Let's see what the books find today. Here's Lefschetz, the analytical geometer. So, and then there's maybe some Kodaira. So Lefschetz is like one of this great analytical geometers and getting to the singular theory. So when we were reading from Neri about singular integrals and the convolutional setting about when it's like, well, this integral system works great, but we need the transpose to come out of it instead of using the transpose to cancel it out, and cancel out its terms, and because it's like 90 degrees opposite from where it should be if we're going to figure it out. That the singular integrals in these regular singular points, the hypergeometric, 0, 1, and infinity, have a lot going on with respect to then these same kinds of systems, and they would end up being kind of relevant among all these various usual notions of the infinite series that have so much a contribution to numerical methods, whether it's Newton's method, whether it's Maclaurin and Clairaut, as for Taylor and Fourier, respectively, about Gauss and these hypergeometric series, and all these other things that have up front what makes for then either the telescoping or scaffolding or prototype series completions with real analytical character and rigorously, demonstrably, and these kinds of things. So algebraic geometry, the geometry part has a lot more to give to the much nearer to the geometrical solutions than the usual dimensionless algebraic approaches, which, though great and something that very well translate to matrix multiplication and thus basic linear algebra subroutines and such, or the Fortran, or how you might want to put it, with regards to usual fixed precision or floating point precision arithmetic. Something to be said instead for extended precision or the interval arithmetic and the modeling of bounds and so on, and any of these numerical methods, which are only approximations, that computer algebra systems can do any mathematics once programmed that a human can do by just manipulating symbols, not necessarily their literal numbers and scalars, which is what numerical methods do. That's routine vis-a-vis that which is analytical itself. So it's a pretty great book, and I have barely begun to read some first few pages, but its initial concepts, being it addresses a whole subfield of mathematics, are key and critical to have in mind, because then for when there's things going on like, well, I got arithmetic and it's usual and natural and its laws are arithmetics, but it's also broken down to have addition and division separately, and they come together in the middle somehow. They would build something that looks not at all like both of them together from either side. Neither is they doing the extension from one to the other, but it does in the middle. Or to have it so that's like, well, how are real numbers built? Well, first you got integers, and then you break it down in various different ways until you got the real numbers. And it's like, well, what if instead we start with the real numbers, and then the integers are what just arise in the middle? Oh, you mean there's a totally different theory where one of them, the integers are primitive, like number theory, and the other one, these continua are primitive, like real numbers, and either of them arrives at to model the other, but in either one of them, the other one's a completely higher order construct? Yeah, it's exactly how it is. It's kind of the same for like set and part theory. It's like, well, in one theory we got sets, and the other theory we got parts. Just like that addition and division thing I was just telling you about. And then, for algebra, it's like, algebra, which algebra? There are great algebras that have all their inverses and identities, and there are ones that only have half of those. And there are ones that they have both halves, but they come back opposite ways. There's all kinds of them. So which one, is like, among all those, then which one is it? Well, it really just mean like arithmetic's numbers. It's like, why didn't you say so? It's like, well, it's an extra line, It's like, yeah, well, I guess it isn't. Yeah, and these kinds of things. So there's arithmetic and algebra and geometry, and for number theory. And then topology is like between these and those, we got topology somehow. And then function theory. And then function theory is like, hi, I'm from logic. I'm a matter of relations, terms, or predicates. You can pick one, but if you're going to be general, it's relations. So you can call me function theory. And I'm the same in logic and mathematics too. Again, I'm usually much higher order construct than the primitive, primary, and fundamental objects of our counting and numbering, which aren't even primitive in terms of each other, yet higher order constructs in terms of each other. That's somehow given only one theory, that all the elements, the primary and primeval and elementary elements, that that's all one model for all the theories put together. And it is. And that's perhaps the greatest thing about mathematics that are just defined by relation, is that one way or the other, there's a theory with just one relation, and then everything builds out of that. So the axiomatic set theory is, after kind of an axiom-less set theory, it's just like a theory about relation, that its foundations as from, nothing pretty much or else. It's pretty great then that ends up being a common theory by all means. Then it's called Platonism, but really it's just kind of a stronger mathematical Platonist, stronger logical positivists, stronger axiom-less induction of a true theory, that there is one at all, a theory. and it's a theory. This is how it goes. So let's see then. We got some talk about the swath, Zenos swath, and how that's going to be trying to figure out how to solve these quadrature-related problems in the quadratic with these cubature-related issues with regards to the infinite dimensional in terms of frameworks kind of similar to thinking what goes on in changes of directions or transitions in regimes, like the analysis of the Big Bang, using that as a model of reasoning about something that doesn't really have a beginning or end and fit in the data, an exercise in model fitting in a sense, to help arrive at the basic way to break these things down like into modes, principles, majors, minors, and the long tail. That being a way to describe what otherwise is usually called normal, the bell curve, Gaussian distribution, rather kind of explaining that they're classical and non-classical, linear and non-linear, and standard and non-standard things in these. For that, probability, of course, is defined by the law of large numbers, and when there's more than one, it's defined by the laws of large numbers. With regards to usual counting arguments and estimators and the likelihoods and estimators given random variables, and a theory of all this, where it's like after our axiomaless mathematics and logic arrives at something that's true, at least, then we got science above that, and science and probability go hand in hand together, definitely, because they are much the same thing, the analysis of probability and science with regards to science having basically the stronger bar of like falsifying is like, I don't know about probability, but one counterexample means it's not so. It has to have something else going on, or those become new theories, the empirical and all this kind of stuff, the empirical and then the empirical. So then that's having basically wrapped up to where we're talking about Zenos swath is after moment and motion in meters per second, seconds per meter, and both. And then for the dimensional and dimensionless alternator and resonator, everywhere, all the time, because it's a sum of history, sum of potentials, because energy, however conserved, is only one quantity at a time, or a transition. And it's exactly this kind of transition that dynamics is kind of trying to figure out how it makes the corner of these things. That's how it is. That's how it's been going. So, yeah, if there was a study of probability theory, then in hundreds of years ago, then it was usually matters of chance in cards or dice. Either one of which, of course, is a fool's wager, because the martingale guarantees that nobody can beat the house, and then that otherwise it's a zero-sum game, as it were, compared to making use of probabilistic estimates to gain actionable intelligence, to use activities of the intelligence, which can go faster than the speed of light. I mean, you can plan and set up there all day and be ready for something when it arrives, according to intelligence. That then the other study of mechanics was the billiard balls, or pocket billiards of mechanics. And this is basically a game of a table game, according to that on the table is felted or even slate sometimes, and that is the field, and then the players or the balls are perfectly spherical balls. They're originally made of kinds of ceramic or bone, in terms of that they're perfectly inelastic when they collide with each other, that there's mostly zero energy loss to their deformation and reformation, and that their deflections were entirely geometrical. And so the billiard ball mechanics is like, well, how does it start? How does it stop? How does it slow down? How do they interact and reflect? How does striking a rack carry the force out through the rack of the balls? I mentioned this one time before, but there's in America there's snooker, but there's basically 8-ball or 9-ball, and they're usually on regulation tables, but then there's shorter tables or bar tables, or bar pool, and a ball in hand, and 8-ball, and 9-ball. And so in this game, the point is to sink the final object ball, which is the 8-ball and 8-ball, or the 9-ball and 9-ball. But it's got to follow in sequence. All the other balls have to be pocketed first, or else it's considered a scratch, which on the 8-ball or 9-ball, it also equates to a loss. Although usually in 9-ball, the 9-ball would just be spotted if it's sunk out of sequence. Whereas in 8-ball, that scratching on the 8 or sinking the 8 before its time equals loss. So anyways, on the break is the very first shot of the game, and the 8-ball or 9-ball is buried in the middle of the rack, which is an alignment where all the balls in a good rack are set together so they're still in at rest and touching. And usually in a triangular formation, or as a 9-ball in the diamond. So when you make the break as the initial shot, it's from the other side of the table, and you use a stick and you strike the cue ball with the end of the stick, and such that the cue ball then proceeds to roll into the other balls, and then it strikes them, and then there are these pockets are spread equidistant around the table at 6 points on the corners and the two longer sides of this rectangular table. Right? So on the break, you have to strike the front of the rack with a break. Usually it's the 1 ball is in the front, the 1 or the 2 balls. So when you strike that rack, it's possible via the configuration that the 8 or 9 ball, though buried in the center of the rack, makes its way to a pocket and is pocketed on the break. So much like sinking the ball not at the end results a loss, sinking the ball in the break results a win. And so you can win billiards, 8-ball or 9-ball, on the very first shot of the game by simply striking the cue, making the break, having the 8 or 9-ball proceed directly to usually the rear pocket, either side, usually the opposite side. So how is it so that all those forces add up? That it's not just a resonance that comes out always random? I'm not sure, and I played thousands and thousands and thousands of these games, mostly when I was a youth, and we had a pool table in the basement. But hundreds and hundreds and hundreds of games, 20 or 30 years ago, and every 20 or 30 games, it's sink the 8-ball on the break. So it is definitely possible to arrive at a otherwise highly contrived situation. We're recording the mechanics of this that could be formalized that a robot arm could do it too. But without otherwise, trying to figure that out, you can't really have said that it's figured out at all. And it takes a lot of practice then to be able to pick it up and put it down. So that's just an idea of that. That's where a lot of the theory of probability and mechanics had come from. And that said, it's just kind of just a not very important content about the mathematical context here mostly overall, except that if it's lacking in experience, sort of real-world experience with analog things among the digital milieu, then it would sort of be expected that there wouldn't really be a conception of the analog world at all. So that's what I was excited about to learn, is I could sort of apply the theory that had gone to model fitting of Big Bang theory, or these days kind of a big boom theory, because it's some kind of cyclic cosmology, because, well, even if some aspects of inflationary theory can still be around as from when something arrives from nothing and a true origin of the universe kind of could be a thing, but the whole rest of the expanding universe theory and inflationary universe theory is just kind of like, that was model fitting to a not relevant thing in the overall thing. It's just no longer accurate, all these numbers that it would be estimated that, at 10 to the negative 32nd after the Big Bang, then X% was plasma and X% had reached a different regime. Not that ever really added up to anything except confirming the observations, as it were, overall. I don't know if they call that doing physics, but it is making work in a sense. I just don't know if it's doing work in a sense. Well, all right then. I've kind of puttered out here a bit at the end of this one. And so I suppose that as summer goes on and arrives and catches everybody up in the activities of summertime, that I'll look to continue a bit more on this idea of the swath integral. And Zenos swath being kind of a higher order development and an extension of the same analytical deductions that are necessary to arrive at an intuition and really a true and non-hypocritical formalism of real analysis. That then the goal would be to reduce that then to the parts so that it fits on a page or only a few paragraphs more or less, and then analytically as well for our analytic geometry and algebraic geometry into formulas and symbols in those of logic and in those of mathematics and in those of mechanics or the units. So then it results in kind of development that then for something like the unit impulse function Dirac's delta, a unit radial basis function, which is kind of like it's a circle centered on the origin, and it's zero from every direction, but when you reach zero, it's a circle of area 1. Non-standard, yet having the same sort of character as if from a point there, a circle. And I know that's a new one, but I just thought of that a while ago. And then these other notions of the original analysis, that then we're going to arrive at something for the infinite many higher orders of acceleration, that they're windowed and framed and put into a box. That then ends up being a way to define for infinite expressions their completions and closures, closed forms, this way helping to arrive at what would be sensible and fungible and tractable treatment for a zeroth order, zeroth laws of mechanics these days. So if I've forgotten that, or if somebody already invented all that and it has it so briefly, I'd be really interested. And I hope I would have heard of it by now. Hey, have a great day. If you would, if it is, good luck.